awareness of them is relatively recent. So like science fiction and common logic makes it seem like an inevitability that they would exist, but we haven't really had evidence until relatively recently. The first evidence of an exoplanet actually dates back to 1917 from Mount Wilson Observatory. They only found records of this in Carnegie recently, but at the time it was thought to be something else. So no one really knew that it was an exoplanet, and it was brushed off. But the first scientific detection didn't occur until 1988 with gamma Cephei AB. Still, even then, some astronomers were skeptical, so gamma Cephei AB was only confirmed as an exoplanet in 2002. But the first confirmed discovery of an extrasolar planet goes to PSR B1257 plus 12 in 1992. So this is kind of the history of the exoplanet discoveries. So you can see that there's not really much there. Doesn't mean that there wasn't there, it just means that lately we found a lot more. So they're not going to really show you the little ones and twos that happened. You can see a blip on 1996, and then a steady growth, and then bam, 2014. It should be noted that the Kepler Space Telescope, NASA's Kepler Space Telescope, which they're using mostly to find extrasolar planets, got started in 2009 to 2013, and they're still analyzing data. So that's mostly from Kepler, as far as we can go. Okay, as you can imagine, planets are quite difficult to detect, even in our own solar system. Neptune itself was only discovered in 1846, right, Brendan?
I don't remember years, but sure.
Okay, 46. So how do we find planets in orbiting other stars, which are already sometimes really difficult to see? Unlike most planets in our solar system, exoplanets are difficult to image directly, as the stars they orbit easily outshine them. So the planets are disguised in the glare of their own suns. Many of the methods that we use to discover planets then rely on their parent star for their observations. One of the first methods used to discover exoplanets was the radial velocity method, also known as the wobble method. An orbiting planet causes its star to quote-unquote wobble in space. This causes the observed wavelengths of the star to shift from redder to bluer, as shown in this diagram, based on the Doppler effect. So I don't know how many of you are familiar with it. It's pretty simple. Basically, the effect where waves get stretched out as an object moves further away, then compressed as an object moves closer. Since red has longer wavelengths, the stretched wavelength of a star moving further away shifts into red. Blue light has a shorter wavelength, and therefore a star getting closer looks very slightly bluer. This would be kind of a top. You can imagine that Earth would be somewhere down in this direction, observing from the side. I don't know if that makes sense. Canadian astronomers Bruce Campbell, G.A.H. Walker, and Stevenson Yang of the University of Victoria and the University of British Columbia were the first to publish a discovery of an exoplanet that later was confirmed. They used the radial velocity method. Until 2012, if you can remember from the previous slide, the radial velocity method was the most popular and productive of the exoplanet finding methods. So about 18.1% of exoplanets to date have been discovered using the wobble method, which amounts to about 669 planets. But the most effective method at the moment is the transit method. It accounts for 78.3%, or 2,899 of the exoplanets discovered and confirmed to date. When a planet passes directly between its star and an observer, which is called a transit, and this happens quite often, so this is how we observe the transit method. So, for example, the solar eclipse in August was technically a transit of the moon across our sun. Very easy to observe if you were in the right place. Exoplanets do this too, and when they do, they affect the brightness of the star. This image distribution, it wouldn't dip nearly that much, but it still dips significantly enough that we can observe it in those cases. With extended surveillance, astronomers can find the slight dip that indicates the presence of an orbiting planet. Only after multiple consistent observations do they classify a planet, an exoplanet as confirmed. So the transit method actually tells us a lot about the planet itself as well. The amount of dimming can indicate the size of the planet. The duration of the transit tells us the speed of the planet's orbit. Observing the spectrum from the planet, or the sun rather, can tell us a lot about the star's atmosphere. So NASA's Kepler Space Telescope uses this method with amazing success to make over 2,000 confirmed discoveries between 2009 and 2013, with much more data that has yet to be completely sifted through. The Hubble telescope has also used this technique to observe exoplanet atmospheres, and other telescopes use this, including Spitzer, and before Kepler, even the European co-rope used it as well. Microlensing is another less popular method. It only covers about 1.4% of the exoplanets discovered so far, so about 53 in total. When a planet passes between a star and Earth, the star's light is bent, focused, and magnified by the gravity of the planet. I don't know how well this displays it, but it does end up focusing to a certain degree that we can measure this as well. Direct imaging is a relatively recent method, making up only 1.2% of confirmed exoplanets, or 44. It involves removing the glare of the star that the planet is orbiting, and allows astronomers to observe the light from the planet itself without being outshined by its own star. This seems kind of obvious to me, but I guess it's challenging to do. NASA believes direct imaging is the next big step. They already have projects planned, including the James Webb Space Telescope, currently under construction, and WFIRST, which stands for the Wide Field Infrared Survey Telescope. There are other methods, and there will no doubt be more as astronomers get more inventive. So far, the results are negligible compared to these methods. So why are we doing this? What are we looking for exactly? This is all very exciting and interesting, at least to me it is. After all, the real excitement comes when the announcement of an Earth-like planet exists. But specifically, we're looking for signs of life in the universe, right? Or somewhere that we can go. What would these signs be, and how can we see them? Everyone's probably heard of the habitable zone, or the Goldilocks zone around a star. It's fairly straightforward in theory. From what we understand about life on Earth, it relies on at least one thing, which is water, specifically liquid water. So the habitable zone is determined based on the distance from a star, which is ideal for liquid water. So we don't want it to be too close or too hot, in which case the water would turn to vapor. We don't want it to be too far, in which case the water would be ice. We want it to be just right. Depending on the temperature of the star, that could be relatively close. For cooler stars, as you see here, the scale goes down. This is a cooler red dwarf. And then for hotter stars, it could be further away. It could be more expanded. So another thing that we consider is the planet's atmosphere, which we can investigate using spectroscopy, the study of electromagnetic spectrum. Part of spectroscopy is observing absorption lines, which occur when a light source, like the sun, passes through a gas. The gas absorbs or disperses part of the spectrum, leaving, or removing rather, a small band of light. These bands of light are very characteristic depending on the certain elements. So if we observe them, we'll know pretty much what elements are in that gas. And this is exciting because atmospheres are made of gas. So if we just position a light behind any planet, we can compare their spectral signatures and determine what is in that planet's atmosphere. So when a planet passes in front of a star, like during a transit, which we telescopes can pick out spectral signatures and find out what is in their atmosphere. Once again, we're looking for water here, just like Earth has some water in its atmosphere, but we don't want too much water, which would indicate that the planet is on the hotter side and it's just turning it into vapor. We want just the right amount of water. Other people suggest that we should be looking for oxygen in atmospheres, as without plant life, oxygen would not otherwise be sustainable. It would just kind of go away over time. Some believe that oxygen is an unreliable marker, though, for life, as at different points in Earth's evolution, oxygen was barely present. So if we're looking for potential Earths, it might not show up as much as we want, but it might show up later. Some believe that methane and non-compatible elements being present in the same atmosphere would suggest life. So bear with me on this, but oxygen and methane, or methane and carbon dioxide, react in such a way that methane eventually disappears, far from what I understand it. One of the ways for methane and CO2 to be present in the same atmosphere is because of methane-producing organisms. So if we see a sustained methane and CO2 atmosphere, it means that there's probably methane-producing organisms, like life. Another theory suggests that we should look for burning hydrocarbons or smog in the atmosphere of exoplanets, and I found this quite compelling because it's really easy to believe that extraterrestrials can be just as stupid as humans when it comes to pollution. Of course, all of this is great, and the debate is ongoing about how we can find other signs of life as we know it, but what about life as we don't know it? We've seen a lot that we never thought possible, so it's entirely likely, even probable, that there is life out there that we could not even compare ourselves to, which is why there might be signs of life that we don't even recognize. Things that we don't notice are signs because they are so alien and different from our own ways of life. So at the moment, we don't really have a good grasp of the chances of finding it because we don't know what other variables are out there to take into consideration. So what have the results been so far? A brief summary from NASA's exoplanet website, which I posted there because it's really cool and you should take a look at it. Gives some quick numbers. They have a really interactive and comprehensive site where you can get all sorts of interesting information, including some very good graphics that help explain the different exoplanet finding methods. Definitely check it out if you have a minute. But here are some of the numbers they gave me when I last checked at the beginning of March. So far there are 33,705 confirmed exoplanets. This means that they have been observed multiple times. These confirmed planets are orbiting 2,760 different stars. A further 4,496 exoplanet candidates are awaiting 100% confirmation, though NASA claims they sit between the 80 to 90% probability. With results like this, many believe there is an average of at least one planet orbiting every star in our galaxy, which would mean over 1 trillion exoplanets in our galaxy alone. Additionally, some estimate that there may be over 1 billion rogue planets in the Milky Way as well. However, not every planet we come across has potential for life. Of course, of the confirmed planets, 1,483 are classified as Neptune-like, which I take to mean they're ice giants. 1,211 exoplanets are classified as gas giants, like Jupiter or Saturn. Of these, some will be hot Jupiters, which means they are gas giants that orbit extremely close to their parent stars, sometimes taking only a few Earth days to complete a rotation. 929 of the confirmed exoplanets are classified as terrestrial or rocky, like Earth, but also remember that Mars, Mercury, and Venus are also considered rocky. It's exciting to hear this in relation to exoplanets, but just because you can stand on it doesn't mean you can live on it. 55 are super Earths, which sounds really cool, but mostly just seems to mean that they range in size between Earth and Neptune. Anything beyond that definition I was not entirely clear on. from their website. Also, a mystery would be the 27 unknown exoplanets, which presumably just have not been investigated enough to be classified yet. So you can tell kind of how they're broken down. Terrestrial does make up a considerable chunk though. So that's, optimistic. Okay. Well, where have we been finding exoplanets? This is a screenshot from the program Eyes on Exoplanets. So if you remember, Chris Keller talked about this program last time. It's really cool, and I took a lot of time exploring it, and it came as perfect timing, so I was just getting started on the presentation. But this picture shows most of the stars that we have found, have exoplanets orbiting them. It highlights them at least. The sun is in the middle of this bright patch, right? And as you can see, there is a very distinct pattern here. Those stars with exoplanets congregate directly around Earth, or radiate out in some kind of cone-like shape. Of course, this doesn't mean that Earth is the origin of any planet in the universe, but rather that these cone shapes are representations of where we've pointed our telescope the most. Specifically, NASA's Kepler telescope. So obviously, we've taken a very close look at this direction here, and Kepler also looked there and there a bit all around. But the conclusion then is that exoplanets seem to be everywhere in our galaxy. So wherever we look, we'll find them. Logically, this is probably true for every other galaxy out there. This picture is more zoomed out and shows all of the exoplanets discovered to date in our galaxy. The closest exoplanet to us orbits Proxima Centauri, a star only 4.22 light years away from us. The furthest confirmed is Sweeps 11 and Sweeps 4, which is 27,710 light years away. Though some claim to have found evidence of exoplanets in the Andromeda galaxy, which is about 2.5 million light years away. And a team of astronomers claim to have discovered a group of rogue planets in the quasar microlens RX J1131-1231, which is 3.8 billion light years away. Okay. But what are they like? This question is probably one of the hardest, honestly, not just because talking about literally alien planets that challenge human imagination, but because there are a lot of them. And even then, they all seem to be different in their own way. In fact, it might just be easier to talk about the extraordinary cases or the extreme cases, which demonstrate exoplanet diversity. Before I continue, I should note that the pictures in these slides are all artist conceptions. I'm aware of that. So obviously, they're not from direct observations. So don't bother trying to point it out to me. Okay, exoplanets range in size from 6.9 times the radius of Jupiter, like HD 100546b, to as small as Kepler 37b, whose radius is 32% that of Earth's. They range in temperature, is also enough to make even a Winnipegger cringe. Kepler 7b is a hot Jupiter-type planet orbiting its star in just 5 days, which makes it tidally locked, where the same side of the planet is always facing its sun, and as such experiences blazing temperatures on its day side and frigid temperatures on its night side. Side note, it also has a density of styrofoam, apparently, and it's one of the least dense planets found so far. The coldest exoplanet, according to Wikipedia, is OGLE 2005 BLG 390LB at just 50 Kelvin. Exoplanets also keep unusual hours with a wide range of orbital periods. 55 K3b, for example, orbits in, is that Cancer? Okay, orbits in just 0.7 days, so about 18 hours. And it is also tidally locked. Its day-side experiences temperatures of about 2400 Celsius, while its night is about 1100 Celsius. Similarly, the entire system around Kepler 11 consisting of 5 planets could all fit their orbits inside of Mercury. The longest orbital period for an exoplanet seems to be that of MASS J2126-8140 at 1 million Earth years for one orbit. Another exoplanet, HD 80606b, has been observed following a heart-shaped orbit. Some worlds are believed to be entirely covered by oceans of liquid water, like Kepler 22b is believed to be. Others fit into science fiction, like Kepler 16b, which orbits 2 stars, just like Tatooine. It's called a circumbinary planet. The exoplanet HD 126614AB, are you guys writing this down as you is located in a triple star system. And just when you thought you knew it all, nature throws a curveball in the form of one strange planet known as WASP 12b, which is actually egg-shaped, distorted by the gravity of its star. All of these exoplanets are confirmed to exist, as outrageous and as unbelievable as that may seem. One discovery that has certainly grabbed a lot of attention lately is the TRAPPIST-1 system. NASA announced the discovery of the TRAPPIST-1 system on February 22nd, 2017. TRAPPIST-1 is a system of at least 7 Earth-type planets. It is the largest batch of rocky Earth-sized planets orbiting at a reasonable distance from its sun. Scientists believe that it is a promising candidate for life, so it has been studied extensively, more than any other planetary system apart from our own. The system of planets labeled TRAPPIST-1b through H orbits a red dwarf star, so they orbit very close to each other, and their parent star, so that even TRAPPIST-1h's orbit, the furthest away from the sun, would fit inside the orbit of Mercury. Oops. Look at inside the orbit of Mercury. And that's kind of the scale. But because it's a red dwarf star, so much cooler than our own sun, these planets lay at a distance that some would call the optimist's habitable zone. This pretty much means that the closest planet would probably have mostly vapor water, or water vapor rather, and the furthest away would be more appropriate for ice, while about 3 of the planets would be pretty good candidates for liquid water. That's E, F, G. It's considered the optimist's habitable zone because maybe some of the planets could be fudged to fit into the green area. So this is a group of planets that all have the potential for liquid water and may contain more water than Earth's oceans. It's no wonder it has encouraged some interesting artists' rendition. Great news for those wanting to partake in this planet-hopping adventure. TRAPPIST-1 system is only 39.5 light years away, so if you hop into your roadster, it'll only take you 441 million years to get there. So TRAPPIST-1 may be a bit too far to get to at the moment, but there are other ways to get involved. There has been a great move towards crowdsourcing in the sciences now, and exoplanets are becoming a large part of this. No doubt most of you have heard of SETI, or the search for extraterrestrial life. Well, SETI at home is a scientific experiment based at UC Berkeley that uses internet-connected computers in the search for extraterrestrial life. So you can participate by running a free program that downloads and analyzes radio telescope data. Something more exciting would be the website Zooniverse, which has a number of disciplines to look at, but if you check out the space section, it has 2 exoplanet missions that I found. Exoplanet Observers provides data from NASA's Kepler Space Telescope to give you the opportunity to find exoplanets using light curves. It gives you a brief tutorial about what you're looking for and a field guide with examples of good and bad candidates, as well as what that all means. Planet Hunters is another mission they have on Zooniverse, and it also uses data from NASA's Kepler Space Telescope and gives another tutorial. This one I found more user-friendly than the Exoplanet Explorers, but that's my opinion. And it tells you how to mark transits and it gives easy to read information about the star itself. You can also choose to sign in to receive credits for your observations. I don't know what the credits do, but they're apparently enticing. In both cases, your selections are compared to other volunteers to provide sound conclusions. So you're not given a lot of responsibility, just some involvement. And there have been some results from these. In January of this year, NASA announced that as a result of exoplanet explorers, scientists, or citizen scientists, as they've been called, have helped discover a multi-planet system that may contain up to 6 exoplanets. They've named that system K2138. So there's a lot of exciting things to look for in the exoplanet kind of field, and I am going to go home and go back to Zooniverse later. All right, any questions?
Thanks, Sarah. An entire night to clicking circle, like marking where little light dips are on light curves, you haven't lived. It's pretty fun and really addictive. So I do recommend going to check out one of those projects on the universe. Definitely worth it. Anyway, my name is Brandon. I am the somehow current president of the Winnipeg RASC. I'm still waiting for that thesis investigation to conclude, but until then I'll be around. Are there any new people out tonight? Hey, welcome new people. We do have a refreshment break. Feel free to come down and say hi. Alternatively, are there any council members here tonight? All right, sweet. New people, say hi to the council members. You guys should connect. Hi. All right, cool. So our agenda for tonight, we are going. Well, we just had Tara give us that nice talk on exoplanets. I've got a bunch of announcements to go through. I hopefully won't spend too much time on them because Jay's back, and he will be giving us. He will be. I don't know if he's going to own it entirely, but he wants to start up a new monthly talk called Lost in Space, which will be looking at some of the lesser-known spacecraft that are orbiting around the solar system. Maybe some spacecraft you haven't heard from in a while. So, looking forward to that. And as usual, Brian will be giving us a what's up. So that's what's up in the night sky. And Ian Cameron will be giving us what's new, which is what's new in the science of astronomy. And then we'll have a refreshment break. And then we actually have a very special guest. Paul Gray is here all the way from the East Coast. So, looking forward to that. So, you might be wondering, Brendan, why are you showing me pictures of a wedding? Well, if you've been to some meetings in the past, you would have heard that I was looking for people to do an outreach event at a wedding. This was really cool. These folks reached out to the club. They said, we would like to have some telescopes out, and we'd like to do some observing. They were at Fort White. Got some really nice pictures. It was a beautiful day. But they wanted to have some telescopes out. They told me that they actually, like some of their first dates were going out to, Birds Hill Park and watching shooting stars and that sort of thing. It was really sweet and cute. Right. So, how can I say no? Also, they donated some money to the club, so how can I say no? But wonderful people. We had a lot of fun. So, Kathy and Kevin, you guys are up there? Yeah, so they came out with their telescopes and helped out. Big thanks to them. And we had a blast. It was great. It didn't look all that great, but things managed to clear off. And yeah, it's Fort White. We still got the soup, but people had a blast. They really loved it. It was a very unique kind of thing. So I just figured I'd relay that. We had a lot of fun. It was cold, but we had a lot of fun. We've also got this. This was sent to us via the U of M. There's a public lecture happening on March 23rd at 3:30 in this location. It's being given by Virginia Trimble, and it's basically on multiverse stuff. So if you're into that kind of cosmological thing, it'd be worth checking out. Unfortunately, it's on a Friday. I'll likely still be at work, but I might have it early. But yeah, I recommend going and checking that out. I will, if you don't have a writing implement or anything like that, I'll throw this up on the website and I will send out an email about it. So, the great courses. I was approached by Mick a little while back asking about the possibility of running through some of these astronomy courses with a group. He had done it previously with the astronomy club in Sault Ste. Marie, and it was a pretty good hit there. And so what the idea would be is that rather than, so in addition to our main meetings, the idea would be that we would have another night of the month set up where we would go through one or two lectures of these great courses. Just out of curiosity, just so I can kind of gauge like where should we be going, just by a show of hands, and you're not committing to anything, because we can try to get a room regardless, but I'm just curious, like, what's the general sense of interest by a show of hands in doing something like this? Okay, cool, yeah, okay, that's good. Yeah, that gives me what I need. So I think what we'll do then is, I'll probably send out an email. Just trying to, and we'll just do a bit of a sign up. Maybe, I mean, you don't have to sign up, but I'd maybe do a vote on which course we want to do, and then we'll just pick a date, a time, and a place, and we'll start going through them. Okay? In addition to these astronomy ones, there's actually a whole series of other ones. What kind of neat? Anyway, moving on. So the RASC 2019 calendar, you should, well, several of you have the 2018 calendar. You should all have the 2018 calendar. It's quite nice. Although there's some shot by some guy named Kevin Black in there. It's kind of neat. I don't know how he got it in there.
I've seen yesterday.
Yeah, he slipped Paul some money. So anyway, this is also kind of timely because you may have noticed that, and when I say submit to Paul Gray as our speaker tonight, don't like drop it off like tonight. I mean, if you did, cool, I guess, but don't print something off and give it to him. Anyway, but no. So the RASC 2019 calendar. So Paul's currently accepting submissions for it. I'll send an email about this that has a considerable more amount of detail in what he's looking for it. But the deadline is March 31st. So I'll get that email sent off probably tomorrow morning. I would say tonight, but after busting pizza, I probably won't. There's also this going on. So it's a contest. I should point out that I don't believe that there's any actual, there's nothing to win other than pride, which is really the best thing to win, right? But it's a cool idea. I really like it. I checked out the website, and basically you can just hop onto the website and submit your stuff, and you can vote on stuff. So it's broken down into two categories. One is geared towards what we're really used to, which is astrophotography and sketching, and then one is creative works. And I don't know. I think this is neat because I'm really interested to see what other kind of stuff comes out. I saw a couple examples, and there's some neat stuff. But I would just love to see, like a stained glass, I don't know, ring nebula or something like that would be cool, right? So if you want to make a stained glass ring nebula, like let me know, because I will just be happy about it. But yeah, so go check out this website and feel free to submit or vote. This is the sad part of the meeting. So effective 7 days ago, the membership went up by $3. It hasn't gone up in a little bit, and we are actually obligated to, we as in the RASC National, like we are obligated to increase it with cost of living and as it goes up. So you'll notice a slight bump in your annual membership fee. No booze. As usual, there is the Oak Hammock Marsh Astronomy Night. It'll be taking place Thursday, March 15th from 7 to 9 p.m. They do an indoor presentation, and then there's some rooftop observing afterward if it's clear. If you are a RASC member who brings a telescope and helps out, they will waive the $10 entry fee into Oak Hammock Marsh, into the Interpretive Center. I didn't actually confirm with Danielle whether she was going to be doing it this month, but I'm just going to throw this out there anyway. She usually sends out an email anyway. But the open house at the Loeb Planetarium, so this is held on the last Wednesday of every month, so just a reminder. But Danielle usually sends out an email just to make sure that we know about it. Telescope loans. So, if you are a member, you get access to our to some telescopes that we have for loan. That's why this one's titled Telescope Loans. If you would like to check one out, talk to Stan Runge, who is somewhere. There he is. Hi, Stan. So Stan is the current sucker who is currently responsible for the telescope loan program. He's actually done a very good job. He's been curating them quite nicely. If you read the Wincentrics, which you should be, there was a nice breakdown of all the telescopes that we have available. So we've got 2 DOBs and a PSD. So I mean, the 8-inch DOB is kind of the classic beginner telescope in my mind. It's super easy to use, but you can hunt a lot of deep fuzzy with it. So definitely, I recommend, like, if you're just getting into it, like, this is a really good way to do it. Is sign up for a telescope loan and take it out and get out into the stars with it. So very, very low effort, very low cost. So definitely recommend doing it. Stan, what's your current status of telescopes?
Both of the DOBs are out. They can be made available for next month if you like, and the solar scope goes out again today. So.
Okay, so they are in hot demand, but get your name in and you can...
Yeah, people can do it from the website.
Yeah, that's a good thing to remind you, actually. Yeah, so if you go onto the website, just use the contact form, and that'll go right to Stan, and it'll get your name on the list. Monthly Observatory. This is another perk of being a member, which your extra $3 a year will contribute to in some way. It's open to all members. There is a warm room there, which has been spruced up a little bit by Brian, and it's got we've got a telescope in the dome, and yeah, if you want to go out there and learn all about it, see Brian for details. He's over there. He'll also be doing the What's Up, so you should recognize him. Also, at Glenlee is where we do our members observing night. So Brian has elected to, I think just because of weather, Brian's elected to do it Sunday, March 11th. So if you'd like to observe with other club members, I recommend showing up on Sunday night. Okay. Also, I was informed that there is a rare alignment of astronomical proportions tonight. Is Ralph here? Hi, Ralph. Happy birthday. Oh. We're not going to sing. But happy birthday, Ralph. Ralph has been with the club for a very long time. He's currently a council member and has contributed greatly to this club. He also provides all of the the gifts that we give to our guest speakers and has organized a lot of them. So happy birthday, Ralph. Thank you. Congratulations on another year around the sun. All right, and with that, Jay, you ready to go? Loaded? Yeah, I'm all loaded.
Those aren't cats.
My mentors. Everything I know about space I learned from these characters. Lost in space. Well, there's a lot of satellites up there that you never hear about. You know, it's well known about Cassini and about Juno and Hubble Space Telescope, but there's a lot of other ones that we don't hear about too much. So I thought, you know, they do a lot of interesting science, so I thought I'd start picking one up every now and then for a meeting and just tell you about some of the more obscure ones. This one is not particularly obscure, certainly not if you're Japanese. Akatsuki had a really interesting adventure. It was launched in 2010 and made a pretty expeditious trip to Venus. But when it got there, its orbital insertion rockets, well, they worked, but they only worked for 20 seconds and then they blew up, which left it in a solar orbit as it sailed past Venus, and they got about 20, 30 minutes of data from the satellite. But they weren't undeterred. They still had the maneuvering rockets working on it, so they adjusted its orbit a little bit and let it sail around the sun for 5 years until it came back to Venus again. And then they used the maneuvering rockets to slow it down and put it into orbit around Venus. It wasn't the orbit they wanted. They wanted one that was initially 80,000 miles high. They ended up with one that went out as far as 360,000 miles because there isn't a lot of energy in the maneuvering rockets to pull it in tight toward the planet. So it's now in I believe it's a 9-day orbit around Venus in this quite elongated orbit, and they started doing observations about a year ago, with a regular science observation. What they wanted to do was look at the structure of Venus's atmosphere. We tend to see Venus in a telescope as just a blank white object. About the only thing interesting on it is that it makes crescents and gibbous phase and everything else, just like our moon. But it has an atmosphere where in ultraviolet radiation you can see some details in it. But for the most part, it's a planet that's believed to be pretty simple. It just rotates very, very slowly. It warms up on the side that faces the sun, and the air sort of flows around the planet and sinks back on the other side. Pretty much an even, very high temperature all around it. They wanted to study those clouds, though, and they had instruments in it that would let them see a little deeper into the cloud layers instead of just looking at the top of it. And from that, they would be able to determine what the wind circulations were in the winds that were going around the planet at higher levels, which they're known to be very, very fast winds, and they actually circulate around the planet in 4 days compared to its 248-day revolution. Anyway, radio occultation lets them see what the atmosphere looks like and temperature looks like, depending on how the radio signal from the satellite changes as it passes through the atmosphere on the way to Earth. However, they ran into a problem this month, not even a year of operation. Their near-infrared cameras had to be shut down when they started getting some erratic cutouts on them. They were a little afraid that they were going to affect the rest of the power supply. The interesting thing about Venus is the data that are collected are dumped into a repository which it's open to the public. So you can actually go in and get the ultraviolet and the infrared images from the satellite, and you can play with them yourself. And so recently, one amateur named Damien Buick has taken on the task of just doing some nice processing of these images and essentially making pretty images out of them. Very quickly it was tied into a couple of scientists who realized they could see a few details in these. So this image is from Damien, and it doesn't show you much more than what we've already seen in Venus. It just shows you a little nicer looking shape. But one of the things that is interesting about this is the modeling in here. We typically are used to seeing these sort of chevron pattern in Venus. This modeling is a sign that there should be some convective clouds. And with this wavelength, we're actually looking a little deeper down into the atmosphere. And convective clouds means that there's heat that's overturning from below, rising up in the atmosphere, the same way that anything from a cumulus cloud to a thunderstorm would do in our atmosphere. One of the more interesting things was when they took a look in the infrared imagery. Now, infrared has the capability of penetrating quite deeply into the atmosphere, and if you pick the right infrared wavelengths, you can see all the way down to the surface. But in this case, they're looking in the middle levels of the atmosphere, and the processing that Damia did started to show these kinds of boundaries like this in among all of the cloud patterns. And quite a distinctive type of cloud in the more northerly reaches compared to the tropical and equatorial region. This zone up here is the area that's in sunlight. You can't really use infrared very much in the sunlight because the sun itself will swamp the signal, so you tend to look at just the nighttime. And they also find boundaries like this when they look at high resolution deeper into the atmosphere. Well, Venus is a planet that's supposed to be all mixed up, same temperature everywhere you go. There's not supposed to be boundaries or anything like that. Particularly something like this that resembles almost a frontal boundary, which means that there's got to be cooler areas and warmer areas on Venus. Probably 230 degrees Celsius instead of 248 degrees Celsius, something like that. So all at once we have to start changing the models that we have of the atmosphere of Venus to try and account for these things. And no doubt now somebody thinking, well, we need another satellite up there to explore these things in more detail, particularly since the two infrared cameras have been shut off that would typically take these images. Again, another one of a picture showing the night side again. And there's quite a few different wavelengths that are observed by these infrared cameras, so you can select the depths that you want to see by the length of the wavelength that you're looking at. So here we see more of this convective nature of the Venusian cloud patterns, and from each one of these little traces here, you can actually map out the wind fields at that level by watching how fast these clouds move. Now you have a very, very long elongated orbit on this satellite, so you only get the high resolution stuff when you're in close. So there's probably only a 2-day period or so where you can really get a good idea of the cloud and how it's moving. If you go online, you'll find some of those movies, and they go on for what seems to be far too short a time before the satellites now move too far away to get the kind of resolution that you'd like to have. By taking two of the wavelengths and constructing an artificial green channel, Davey has been able to put together an RGB composite, which is what these are. Any one of us could do this. It's almost automatic in some of our astronomical image processing software. The question is what colors do you select to represent blue, green, and red, or what wavelengths? Anyway, the clouds on Venus are primarily made out of sulfuric acid, droplets. They're actually fairly high up in the atmosphere. If you were to drop a balloon or a sensor into Venus, you would sort of reach the bottom of the cloud level where you're something like 40 kilometers high. But because we're looking a little deeper in here, we're seeing the 60 to 75 kilometer level in this image. We also, when we start looking at the more northerly regions, we start to see these other structures such as this. There is a vortex similar to just about all the planets that seem to have polar vortex, including our own, except that it's over Nova Scotia tonight. But anyway, what we're seeing here is something that almost resembles the kind of clouds we see in a jet stream. We do know that Venus has some extremely strong high-altitude winds, and this might be the boundary along one of those wind streams. Certainly if I saw this on the Earth, that's what I would call it. Another thing they found is what looks to be like, I would call them wave clouds. That's a little bit too simple definition for a scientist, so they call them gravity clouds or gravity wave clouds. But we get the same thing on Earth here. Here's a picture of the flow over a number of small islands in the South Pacific. And you can see how the flow over those islands is generating wake waves, similar to the way flow in water would generate the kind of waves as it went over a rock. The thing is that these sort of waves in Venus are not all that uncommon. You can see them sort of one here and then a number of them tapering off here. When you look at different wavelengths in ultraviolet, you don't see them. You only see them in this infrared. And here are several pictures taken over a several day sequence, and you can see that even though the planet is rotating, this arc stays in the same place. When we see that, we typically say that it's connected to something on the surface. The surface is a long way down here, but it does turn out that this wave is directly over top of one of the highest features on Venus, Aphrodite Terra, which is a very, very high mountain range. So there's some suspicion that this is actually the same kind of wave flow in Venus as the air goes over top of the higher terrain. The problem is that Venus surface winds are extremely light, a few kilometers per hour. So now again we have this other problem, is that we don't seem to understand the circulation of the winds in Venus well enough to be able to explain this. It shouldn't be happening. So we either have to figure out another reason why it's happening, or we have to bring in some stronger winds at some middle layer in Venus in order to obtain this kind of a pattern. When we take a look at the ultraviolet measurements and sort of trace out the wind speeds in Venus, for years we've known that we have on the daytime side a very high wind flow that goes around the entire planet in 4 days. But when we look at the night side, that wind flow has kind of slowed down and broken up somewhat into a little more chaotic flow. Again, it doesn't fit with any of the models we have on Venus, so everybody's going back to the drawing board now to try and figure out just what the temperature and wind structure is in the planet. Something that was supposedly one of the simplest planets of all to model, because it doesn't rotate very fast and it's got a very dense atmosphere, all of a sudden has all of these complications in that atmosphere. And then most intriguing of all to me is this structure, which turned up in the mid-levels. When I see one of these on Earth, that tells me it's a low pressure system circulating with, in fact, I would have a low in here and I'd put a cold frontal system running around here. If I was looking at this on Earth, I'd say it was in the southern hemisphere too, because it's going backwards. So what's happening here? We see these all the time in the Earth's atmosphere. I mean, they're ubiquitous. Here's one right here. A big low pressure system centered in here, cold front, warm front, that sort of thing. And all of a sudden we see this structure in Venus. We've seen them in Mars, see them in Jupiter, see them in Saturn, but we've never seen them before in Venus. The atmosphere is not supposed to be able to create frontal systems and weather systems like this. Only one picture showing that. So somebody's going to start having to look for those again. It's never been seen before or since. So, and now the cameras are turned off. So another good reason to go and send another satellite to Venus. So there you have it. The satellite we don't hear too much about, which is actually generating a lot of nice new information about a planet we thought was completely solved before. Thank you very much.
Yeah, leave it to Jay to go storm chasing on another planet. Actually, it's kind of important. I think I might be mistaken. I don't know if they've done all their final cuts yet, but I think that I think NASA in their selection process for the next space probe that they're going to be setting up, I don't think the Venus one made it. I think the Venus one got cut. NASA space policy. I can knock your ear off for it. I don't recommend it. Okay, so I will hand it over to Brian for tonight's What's Up.
Thank you, Brendan. Okay, so we'll talk a little bit more about what's going to happen for March. Where's that pointer? All right. Okay, I'm going to try something a little different this time. Can everyone hear me?
Yeah.
All right, good. Sorry?
17?
2017.
Okay, it doesn't change much.
Right, okay, so sorry about that. That's supposed to be 2018.
Oh man, we're gonna hear about the eclipse. We're looking forward to it.
Okay, we're going to start off with the planets. I'm trying something a little different, a little more animation to my presentation this time. Ooh, a little too close. This is something that Chris mentioned, that NASA, Eyes on the Solar System. It's a really neat program. I'll talk a little bit more about it later. So we're going to start off with Mercury. So a lot's happening with Mercury. One thing that's nice about Mercury, it's going to be really easy to find with the help of Venus. I did shoot out an email, was it Wednesday, about me observing it. So you'll be able to find Venus, and through your binoculars, with the field of view of binoculars, should be able to see Mercury. Mercury would be on top, Venus was at the bottom. It's kind of like a little red dot, but it was nice to see Mercury for the first time. So that's the brightness currently right now on Friday. All right. Now, it's going to remain in the field of view of binoculars for probably, I think, next week, and that's about it. Venus, well, it's still an evening planet right now. Brightness is currently, today, as of today, it's going to be, sorry, that's wrong. That's supposed to be plus 3.8, not minus.
No, minus.
Minus.
That's
Is
correct.
it minus?
Yeah.
Okay, so I was right. Okay, sorry. That's plus. No, that's right. No, it's right. It's minus because, see, I'm trying to say it. Apologize for that. Okay. Again, it's a close conjunction with Mercury. So again, it'll be easy to find Mercury. So, next we'll talk a little bit about Mars. We're catching up on Mars, so this is a good year. Yeah, I can see how this is going to go. Is that you, Stan?
Nope.
All right. Moving on. Okay, so much is going to happen with Mars. Mars is going to be pretty much a morning planet. Same thing with Saturn and Jupiter. The brightness is only 0.7. Of course, at the end of the month, it'll catch up with Saturn. Okay, moving on. Next, we have Jupiter. It's going to be stationary today, but eventually it's going to begin its retro motion. Current brightness is minus 2.1. As for Saturn, well, much is not going to happen. It's going to be pretty much rigid. It's going to stay where it is in the constellation Sagittarius, and the brightness is currently 0.6. I really like this program that Chris mentioned. This is really neat. Anyways, okay, that's Saturn. Next, we'll show you kind of a top-down view of the planets. So we are astronomers, so we should have a really good idea of how it's going to look in the solar system. So you can see Mercury and Venus is off to the left-hand side with relative to Earth. Of course, Mars will catch up on Saturn, and that's going to be really pretty fast, if you ask me. Jupiter's not going to move, and neither is Saturn's going to move for the next time. I don't usually talk about Uranus and Neptune because you can't really see them. Well, you can. We like a blue little dot kind of thing, but when I look at my 8-inch dot. Okay, the conjunction happened on March the 4th, and brightness, I think, was, Mercury was minus 1.3, I think it was. I was going to send an email, but of course the storm hit on Sunday, so what's the point? Now, that was on March the 4th. Now, today, this is where they are. That should be Venus, and that's Mercury, and that's how I viewed it within my binoculars. Mercury's pretty bright. It's 0.8. So that was roughly just after sunset. Now for a little bit about Saturn, Mars, and Jupiter. So that should be Saturn, that should be Mars, and that's Jupiter right there. So Jupiter is not going to move. Saturn's going to stay pretty much where it is, but at the end of the month, Mars will catch up or close the gap between Saturn. And this is at the end of the month, so again, there's Saturn and Mars. This is at the very end of the month. And this is a morning, so you're looking at around 6 a.m. in the morning. Moving on, March events. Because as Jay mentioned a couple times, or a couple meetings ago, we do have, for this month, 2 full moons. So I did take note of that. We still have the zodiacal lights on for the next couple of weeks. And, of course, we have our daylight savings time, which is tomorrow, but now we move the Monday, or members observing night until Sunday, which is even better for my case. Of course, the new moon's on the 17th. We have the equinox on the 20th, and then we have another full moon on the 31st. Well, so okay, this is, I mentioned this last time with my meeting or presentation, just a little bit more of the lights. It's just debris left over from the creation of the universe, and the particles varies in sizes from beginning of atoms to the size of golf balls and stuff like that. Of course, the geometry has to be right in order for you to view it. And of course, in this case, it's going to happen in the evening, which should make it relatively easy. If everything works out on Sunday, we should be able to point it out. I'll probably catch up a few pictures of it. Next time it's going to happen is in the fall, but it'll be in the morning. Okay, again, how do you find it? Well, you need a dark spot. Roughly like Sunday, we'll go to Glen Lee, and we'll point it out for you. It's well, just as bright as the Milky Way. Maybe a little bit brighter, I think, but it's, if you look towards the east, where the sun rises, that's when the zodiacal lights will be. And of course, you have to be free from light pollution. If you've got any kind of light pollution, or it's foggy or something, you won't be able to be. And of course, if it's a full moon, it's not going to happen. All right, that's how it looks like. This was back in Arizona a couple of years ago. Well, 2017. That's how it looks like, which is pretty bright. Of course, the exposure was a little longer than usual, so just to stand out, we'll improvise on the lights there. Now, I did mention about the program. I'm really fascinated about this program that Chris mentioned. Learn something about Voyager 1 and Voyager 2. So both launched in 1977. We're going to zoom in on Voyager 1 soon. Oh, there we go. Hey, Voyager 1, that's where it is. Now we're going to spin around, we're going to see a shot of our solar system, see how far it is. And there it is. And of course the speed for Voyager 1 is about 62,000 kilometers an hour, which is pretty fast. But and next we'll zoom in on Voyager 2. And again, they're roughly about the same spot, a little different. Both launched in 1977. So that's a really neat program, Chris. Thank you very much for pointing that out from last time. So that's all I have to say. Thank you. Saturday, about the members' night. We'll probably we'll start around 7:30, I think.
Hey, Brian. Okay. So now's the part of the meeting where we get Ian over here to tell us all about what's new in astronomy, and science of astronomy, but he's just going to have to get his very nice computer equipment set up.
Oh, you're so nice to me.
While we're going through that, one thing I wanted to mention actually. So there was a little bit of confusion there between the plus and the minus there, and what Brian was talking about was the brightness and the brightness of the planet. So when we're talking about in astronomy, when we're talking about brightness, it's unfortunately kind of backwards. The larger the number, the dimmer the object is. There are historical reasons for this that I may or may not get into, depending on how long Ian takes.
I can be as long as
I don't know if we got time for that today. No, he's doing fine. He's doing fine. So for reference, something like, okay, so like a +6 is about as, for most people, that's about as dim as your eye can see in a dark sky. That's about a +6. 0, 0 to about, -1, -2 is kind of some of the brightest stars in the sky. The sun is like a -26. So like this is all on a logarithmic scale, right? So the really negative numbers are actually quite bright. So if you're curious about what that was all about, that's what that was all about. At some point I do a beginner session usually on that kind of stuff. Maybe I should dust it off again and give it. But anyway, but I timed that perfectly apparently. So take it away.
Of course, it gives me another piece of equipment.
Yeah. Sorry, it's not a Mac.
Okay. Everyone can hear me okay?
Yes.
Good. All right, what's new for March? Okay, first thing to do is don't panic.
Bring your towel.
And of course, this is on the dashboard of a rather famous spacecraft. And would you believe there's a paper out on this already? And it's called The Random Walk of Cars and Their Collision Probabilities with Planets. And these are the folks at the University of Toronto. And they produced a paper, okay, that says, okay, the dynamical half-life of Tesla is approximately 15 million years, so that's why don't panic. And what that really means is that around about that time, there's 22% of the, basically what you have to do is you have to compute orbits for these things. And they, after the first couple, they become a little bit chaotic. All right? So all you can do is compute probabilities. And so these are the various probabilities with collisions with Earth, Venus, and the Sun, respectively. Okay, so you can see that almost half, it's going to collide. Basically half of the orbits that you compute result in collisions after about that period of time. So, just a little bit of fun to begin. This is really important. There's now a detection for the first star formation in the universe. Now that's got to be pretty spectacular. Okay? And as you might expect, okay, these stars will be massive, they'll be blue, okay? And there has been quite a bit of background work over the past little while about how one goes about doing that detection. Now, immediately what you're able to do is actually determine when these first stars are formed. And there's a little bonus there that I'll tell you about a little bit as well. So that means now we can update the timeline for the universe. All right? And so here the first stars are coming to formation around about 180 million years ago. And beyond, after that, basically the signal that you're looking at that's obscured by the existence of black holes and accretion disks and so on. How do you do this? You do this with a little radio telescope. A little radio telescope. Okay, it's about the size of a tabletop. Okay, but the thing is you actually have to stick it somewhere where it's really quiet in the radio waves. And so you end up in the middle of the desert, okay, in Western Australia. This is actually at the Murchison Observatory. And that whole area is a radio quiet zone. And it's designated that. So what is it you actually go about detecting? All right. What you do is you observe the 21 centimeter line in the radio region. And you may or may not realize this is one of the fundamental fundamental ways in which we detect hydrogen. Okay, what you look for is a particular transition called something called a spin flip transition. Okay, when the hydrogen flips its orientation, a 21 centimeter radial wave is emitted. And what you actually look for is not for this line in emission, but you look for it in absorption. Okay, so essentially you've got those stars, you've got cosmic microwave background, okay, you've got absorption, and so this is the line which you look for. But of course the universe has been expanding for quite a period of time, and so what you look for then is a line which is redshift, a significant redshift, and the initial problem is you don't have a clue really where to look for this. All right, so it's the business of looking for a needle in a haystack, and of course the signal is not going to be very strong either, and that was the reason for locating this little, if you like, tabletop antenna out in the middle of the desert where it's really, really quiet. And at the top here, what you can see is basically the amount of redshift, so we're back 150 million years, and you can see that we sort of terminate somewhere around about 250. So if you might recall from the previous slide, okay, we had sort of those limits I had the black hole, holes and the accretion disk, where basically that's when the signal gets obscured. So you can actually pinpoint that very nicely. The bonus that you get, okay, is actually having a look at the amount of absorption, basically this depth. And if you go through the theoretical computations, you find that it's a little deeper than you might expect. And so something else is going on there. And so indeed what it might be is that we've got a little better clue of what's happening with dark matter. And the other interesting thing about that is that maybe dark matter isn't sort of as massive, okay, as we had originally thought. And of course, as people sort of look at this a little bit more carefully, that story will gradually unfold. Okay, second item, or third item, sorry. Okay, it's not a Saturn we know. And that's this particular object here. This is WASP 39b, okay, an exoplanet, which is designated as a hot Saturn. And this is an atmosphere which has been studied in more detail than any other exoplanet. And it has some rather interesting features. And the interesting thing about looking at atmospheres in depth, and actually you can see deep into the atmosphere of this particular exoplanet. It actually has rather a puffy atmosphere, so you can actually see very deep. Is that you can tell something maybe about the formation, okay, of certain exoplanets or certain systems. And here, what we find, okay, is that we have a hot Saturn. It's got a 4-day orbit, so it's 8 times closer to its parent star than Mercury is. It's a little warmish, around about 750 degrees Celsius. It's tidally locked. The interesting thing about that locking, though, is that it doesn't constrain you to a hot side and a cold side, because we have high winds which basically circulate the atmosphere. So it seems to have a fairly uniform temperature around. The really interesting thing about this, of course, it's not a Saturn because there's no ring system detected, okay, is that it's got 3 times the amount of water that Saturn does. And that suggests, in fact, that this planet formed farther out from where it currently is and migrated in. Okay? So these are other kinds of facts that one has to take into account when one is looking at the formation of planetary systems. So what we warning system. Remember, we had a little sort of news note from before. Is that there's a lot more variety in possible planetary systems than our own. And we're probably beginning to appreciate that a little bit more. Now, for the theorists among you, this is really beautiful. Really, really beautiful. And for the quantum theorists amongst you, okay, you probably appreciate now there's a connection between a fundamental equation that one uses in the study of quantum mechanics, and now you can apply it to gravitational disks. The disks which are self-gravitating, so let's say the galaxy size disk of material, you can track its evolution through time in a fairly simple fashion, and, well, let's say it's really suggestive more than anything else. One of the issues that one has when you're looking at modeling things like galactic disks, or indeed any disk around a sort of a parent body, is you usually do it numerically, all right? And so that takes a lot of computing power, a lot of effort. But here is an analytical kind of solution or suggestion that one can approach the problem in this particular fashion. Right? And we know a lot about particular equation, Schrödinger's equation, or Schrödinger-like equations. Okay? And you can start adding all sorts of interesting things into that equation and see where that takes you. We actually do observe warps in the disks often, okay, and so now here, if you like, there's a fairly natural explanation for this. The other thing that one can do, if you're interested in orbits around the center here, is that you can have a look at the time evolution in a fairly nice way as well. So from a theoretical point of view, it's really an exciting kind of result. And of course, the models, as you might expect from this first foray into this area, are fairly simple. I need to provide you with an astro pick of the month, and this is it. Isn't this spectacular? This is the North Pole of Jupiter, okay? There's a cyclone here, and there are 8 cyclones around it. Okay, and these are persistent structures. Right? And of course, the problem this poses immediately is, why don't these things merge? And if you have a look at the South Pole, okay, there's an even larger one around the South Pole, and there are 5 cyclones around that as well. So there's some really interesting things now as we start to probe deeper into the Jovian atmosphere. And so we found that maybe there's something a little bit solid down there at the bottom as well. And of course, if you've got any questions about atmospheric physics, you talk to Jay, right? All right, and that brings me to the conclusion of what's new for this time.
So we're going to take a break for refreshments. There'll be snacks and goodies and cookies and whatnot outside with coffee and that sort of thing. I should also mention that we have a myriad of astronomy magazines that you are free to take with you. There's stuff from like 1988, whenever that was. Historical artifacts. Anyway, so feel free to grab some magazines. It's all free to take, whatever. We'll meet back up here, say around 5 to 9. Alright, your rabble rousers. Wow, we got special guests. We gotta behave ourselves. Sit behave. Come on, Stan, sit down. Talking to you. Good. Stan is ready. That means the rest of you should be quite second by now. Okay, good evening. Again, I've introduced myself 3 times to you. I don't know why I did that. So tonight, we are very fortunate to have a guest from out of town. He comes all the way from the Halifax Center of the Winnipeg RASC. He actually, if you were at RGA back in the RASC National General Assembly that was held here in 2011, I think it was, yeah, 2011. Paul Gray, who's our guest speaker tonight, actually gave a talk on Starmus. His daughter had discovered a supernova and was got this opportunity to go to this event and everything like that. So we had a very fun talk on that. But tonight, Paul will be telling us all about how we can shed some light on dark nebula. So if you could join me in welcoming Paul Gray.
Can't hear you.
Can you hear me now?
Yeah.
All right. Technical difficulties. Thank you for having me. It's great to be here. It's always great to go to other centers within the RASC. I'm actually president back home at my own center. So one of the opportunities I love, or things I love about having opportunities to go to other centers is to see what they do. Find ideas and take them back home and improve our own. So it's been a joy to be here tonight and see some of the many shorter talks we do early on in the evening. So that's great. It's also good to be here to see friends, see some friends I've known for a long time. Stan especially, it's his fault that I'm here. He's been asking me for a number of years to come out and to do this. So Stan, hi. I am going to talk about dark nebula, but it's not entirely about dark nebula. Stan asked me to talk about observing, and he's been after me to do this. So I am going to talk about observing dark nebulas, but also about getting out to get observing. And one way of doing that, of course, is to look back here at observatory. So I got that thrown in here. And I'm going to talk about a bit about imaging as well, partially because it's something else I think everybody can do. You don't need to have the biggest, highest quality in gear to do some basic imaging. And I like to show people that you can do decent stuff with simple stuff. And it all ties together through dark nebula in my circumstance because it's an interest I've had for a long time. And I've found that I can use different techniques and different ways of observing them or imaging them to achieve long-time goals. I've been doing astronomy since 1988. This is actually my 30th year in the RASC, which just blows me away, but it's been a joyous 30 years. So we'll jump right in here, and I'll get into why this all came about. I started in 1988, but I didn't really get into dark nebulas until about 2000. And a little bit of background, it actually, in the early 90s, one of our members in Halifax, Douglas Pitcairn, had a prof from Dalhousie University draw in his lap with Falcon Bernard's photographic atlas of the Milky Way. How many people have actually seen one of those? One of the original ones? Yeah. There's 280, 300 that were ever printed and in circulation. And of those, there's a lot of them that have been bought by art collectors, and the plates and images were cut out of them, framed and sold off. If you can find a copy used, they're typically in the $8,000 to $10,000 US range. So they're not easy to come by. Dalhousie had theirs in general circulation on the bookshelf. So I went in and I grabbed it off the shelf and I went down to them and I said, put this one back, put it in the archives, you don't realize what you have here. And they eventually did, so it's been taken care of. But when Doug got this, he thought, geez, these are great. Look at all these dark spots. You've got to be able to see some of these things. That should be easy to see. So he literally went through the atlas looking for what appeared to be the darkest nebulae in the photographic atlas. If they appear to jump out at you, then contrast is there. If you go and try to observe them, you should be able to see them. I actually moved to the States in about 1998. I burned out in astronomy, sold my telescope that I was in Halifax, and married my wife, and we took off to the U.S. for work purposes. I had a great opportunity in Maryland, and we spent 5 years down there.
But it wasn't long after I got there, about a year and a half after I burnt out in Halifax in astronomy, that I got the bug to get out under the stars again. And I joined a small club in Delaware, got observing, and we had our first child, Catherine. Some of you might know her. She's now 16. She's discovered a supernova. Has traveled around the world. And quite amazing to see where she's gone. But that was my telescope that I bought when I got back into astronomy. It's a total average job. And that's what I've done most of my visual work with in the last 15, 18 years. But we really got to go back a little bit here. I've got to go back to that whole where things started, and that's Bernard's Atlas, because that's really what the project was on. And a bit about Bernard, too. Who was he? Probably one of the great observers of the time. He's done a number of amazing things. He did, the Atlas alone was a great piece of work. And you'll see a bunch of pictures of that Atlas. I'll highlight a bunch of that here in a bit. But he also did other things that he's not known for. But in his early years, as a teenager, he got started kind of in astronomy through another source. Does anybody know what this is, other than reading the fonts there? The local photographer, when he was developing prints and making prints, photos, needed a light source. In the late 1800s, the tungsten light bulb wasn't really that available. So they actually used the sun. And this was actually a large scope, in fact, that would track the sun through a manual guiding and shine light down inside the building and through the projector so they could make prints. Bernard's job as a teenager was to sit on that thing and track the sun. While he did that, he was computing in his head mathematics and orbits and things and learning astronomy, but he was on this because he had an interest in it. But that all came about because as he was doing this, at first he noticed the sun followed a certain path across the sky. And he started studying that in his head as he was doing it. He was able to predict where it's going to go, and he got used to the patterns, and that's where his interest came from at the beginning. So, kind of neat. And that was in our own RASC journal, so you can go back and dig that out of the archives and read the article. What else did he do? He did a lot of stuff. He was a comet hunter. He studied planets. He studied the Milky Way. He bought his first telescope for $380, 66% of your annual income. I'd love to be able to spend that on my observatory right now, but I don't think the wife would allow me. He did discover 16 comets, which is a fair number, given any time in history of the last 200 years of comet hunting. And he also discovered the fifth moon of Jupiter, which is pretty significant. We all hear before Galilean moons, but what about the rest of them? Most people think most of them were done by the space probes, right? But no, the fifth one was visually by Bernard. And of course, Bernard's star. Has anybody ever looked at Bernard's star here? 1, 2, 3, a few of us. I looked at it about 15 years ago, made a little diagram. I plan on going back in 5 years and see how much it's moved. It's one of the few stars, enough proper motion, you can visually observe it, and in 10 or 15 years go back, and it's moved significantly enough that you can say, yeah, it's definitely moved. So it's a kind of neat thing to do. And it's not hard to find. It is in the Milky Way, but it's 9.5 magnitude, so a good finder chart, which you can print off on most planetarium software these days, can get you right into where it's at located. But what he really did the big work that I'd like to study is this photographic atlas, the dark nebulous. And what he did it with was mostly with this, we call it a telescope, he called it a portrait lens. There's actually two telescopes on this. There's a 6-inch and a 10-inch. And the majority of the plates that are in his atlas were done with the 10-inch lens. It provided plates that were, I believe, 10 by 10 or 12 by 12 inches, and covered roughly about 8 or 10 degrees of sky squared. Large swaths of sky. The last I heard, most of the parts of this are sitting in the basement in Mercury. So it's no longer in any shape or form to be used. And from what I hear recently, Yerkes is closing. I expect most of this is going to scrap. So it's too bad. It's a gorgeous instrument. He actually spent 2 or 3 years just finding somebody who could manufacture the optics for to the standards that he wanted. And finally did get it. The other neat thing about that I should mention is the mounting system. It's a standard pictorial, except that the bent base was a kind of an odd design at the time. They're used a little more now, but it was fairly new idea at the time, was to get it off the axis here. So what can you do with it? This is one of the many plates he shot with it, just to give you an idea. This is roughly 120 years ago, 130 years ago, these last plates. So the quality is amazing. Even by today's standards, it's still pretty amazing. The depth he was getting, the magnitude was amazing for glass plates of 100 and something years old from like back around. Their emulsion system wasn't nearly what they had today. And the star images are just fabulous. It's just a beautiful instrument. So this particular plate is down in the southern part of Ophiuchus. And probably the most prominent thing, of course, is the S, Bernard's S Nebula. But there's pockets of little ones everywhere, and then there's bigger ones here. It's just scattered. And if you're trying to get an idea of where this is, for those who have been under a dark sky and looked at the southern Milky Way with the naked eye and seen the prancing horse, anybody? Well, no. Prancing horse is actually here. This is the head. This is the front leg, the second front leg. The body comes back here, and the hind legs are down off the screen. So it's turned up on its side. So you're way down there in the Milky Way for this particular shot. So it's these dark patches in the Milky Way that he was interested in. He was curious as to what they were and tried to see if there was a pattern as to where they occur and how they occur, which is why he wanted to produce this atlas. When we were observing the project the first time in the 90s, and even when I started back in around 2000, there wasn't a lot of resources for finder charts. If you went to the Sky Atlas 2000, dark nimblas weren't on it. There were some star atlases that had dark nimblas on them, but quite often they were just marked with a square or an X. There was no real shape or form. There was really nothing to tell you how much contrast that particular object had, how much opacity it had. Bernard rated his on a scale of 1 to 6, 6 being the greatest. But most atlases didn't tell you that there wasn't any resource. I found the POS, the Polymer Sky Survey, was good for some of them. You can go online and you can access that. And here's the ink spot. We call it the ink spot. It's actually one of the darkest dark nimblas in Bernard's catalog. It's quite easy. It's down in Sagittarius as well. Second edition of the Anniversary of 2000 came out in the late 90s, and it actually plotted all of Bernard's objects. So this was a real eye-opener. It's like, here we go. We finally have an atlas. We can locate them and know how big they are, how much form, what their form is, where to look for them. So this is just a sample of one of the pages of the atlas, and I picked this one mainly because it's got this large, squiggly, dark nimble object kind of on here. This is actually made of B137, 138. I believe this is 343. I'm not sure what the top one is now. I don't recall, but it'll come back later in the talk. But it just goes to show that they are on the atlas. But again, the atlas only goes down to about 9th magnitude. The smallest stars, it doesn't plot them all. So again, you don't really have an idea of, this object is several degrees in length. It's what, 1, 2, 3, 4 degrees tall. So most of us have eyepieces or field of views with our telescopes that are smaller than that. Which part of this should you look for? One side might have deeper star stratum than the other side, more contrast. So it's hard to know where to really go looking. You still kind of have to, snake your way around the star field and try and locate it. The best resource is Bernard's atlas. Problem is like I said, there's only a couple hundred ever printed. And the reason for that is because Bernard was picky. He actually went to the printers and inspected the plates as they were being printed for the books, manually himself, and approved of the ones that were good enough to be bound and put into copies of the book. Anything that wasn't was trashed. By the time he died, he only had enough material for 280 or 300 books. And the book was finally bound and published in a foreword after his death by a secretary. So we're lucky we had the ones we did. They're a gorgeous book. There was actually a 2-volume set, original. One set had the description of the plates that he wrote himself. Mary Calvert transcribed them for him after his death and put it in books. And then on the other page would be your full plate or the image for that area. The other book had a chart, or a table, which listed all the objects that he found on the page or found on that image. Brightest stars, he would name what the brightest stars were, NGC objects from SCAs. name which one those are and highlight it. And then, of course, any dark spots that he was highlighting would be there as well. And then he had the chart that he would hand draw onto a chart what was on his plate. There's actually a fifth plate, which is the image with this drawn on top of it. And we'll see those in a bit too. If you could get your hands on one of these, it's the last thing you want to take out under the dew of the night and observe it. That take your hand. But they were useful. Luckily, the University of Georgia scanned them, put them online, so they're available online. But about 3 or 4 years ago, Sky Publishing got the rights from Georgia Tech to reproduce the book. So this is actually my copy at home, sitting on the bed. It's about 12 by 12, and both volumes are bound into one. A 200-page book. It's fairly heavy, fairly hefty, but everything is there. You got your plates, the charts, the finding charts, the tables, the descriptions. It's a great book. It really is. If you're going to go looking for Bernard's objects, this is one of the best resources. The scale of the plates and the scale of the charts are just perfect for star hopping. They're perfect for getting in there and finding what you want to see and being able to see everything that's on. So I mentioned there's multiple pages for each plate that he shot. This is the page which he would have written himself describing the region of the North American Nebula, which, as you can imagine, looking back at the previous page, he kind of showed you that, and I'll show you the actual plates here. I love his notes. I love reading his notes, especially, for example, the beautiful nebula with the outlining of velocities is in the splendid contrast with the blackness of the sky, which is relieved here and there by bright stars, like lighthouses in a great sea, and by a liberal sprinkling of lesser stars. It's fun to read. It's a joy to read what he was seeing and observing. And a lot of his descriptions are like that. It's almost poetic-like. It's nice. But he's also very good at describing every object that he charted and certain things about each object that can help you if you go to observe them. Following that would be the plate. So this is his plate of the North American Nebula region. There are the objects that most of us would recognize offhand, of course, the North American Nebula, Gulf of Mexico, West Coast, and the Pelican Nebula is over here, just off to the east. But there are dark nebulas in here. This is not one of Bernard's, but this is actually one of Beverly Lynn's from the Lynn catalog. But Bernard actually cataloged this dark spot down here, and he cataloged 352, 353. There's a little one just up in here that he got. And they're all sizes, and this is where it gets difficult. Right in. Little check mark. You think the horse head is tough? Go after this one. It's about the same. There's a challenge for those out there with the big scopes and the filters. Unlike the horse head, this one gets up overhead, so it makes it easier. We've got more or less atmosphere to look through, less distinction, clearer sky. But gorgeous images, though. Just amazing work. I should actually go back to the descriptor page. I think it's on that one. I mentioned glass plates. Of course, it was all manual guiding. He had to sit at the eyepiece and guide these images. At the very top of every page of description, he gives the exposure. 4 hours and 20 minutes. Manually guided. Most of his images are over 2 hours, including the ones in the winter. Taken from Kip Peak, or not Kip Peak, sorry.
Mount Wilson?
Mount Wilson, in the wintertime. He actually almost died of hypothermia one night. He was so cold and frozen he could barely get away from the telescope when he stopped the image. I believe the story is it took him about an hour to get from the telescope and into the building, or out of the observatory down into the building where there was a wood stove, He didn't close the dome, he didn't close anything, he just managed to get himself in there and sit by the wood stove for the remainder of the night and the morning to thaw out. It's lucky he survived. There was another time, which observatory was it? Had the floor that raised up and down. Was that Yerkes? Yeah. He was actually in it the night that it collapsed. He exited the observatory literally within 10, 20 minutes before the floor collapsed. He would have been dead if he was in there at the time. So he was close to death a couple times observing.
Dangerous hobby.
First thing I worry about is coyotes, right? Question?
I had a question about your photograph. With light pollution being a factor today, if we could take that picture, how would it change in today's compared to this?
How it changed, like physically, has the
Yeah,
changed?
as far as the light pollution interference.
Well, yeah, I mean, I think people today, with the technology we have, are doing better photos than this. Even with light pollution, the computers allow us to subtract so much noise and light pollution. Excuse me, neutralize the background and stuff. So, but it is interesting that, you know, to see the development. I mean, 4 hours to probably do the same in 4 minutes if you have the right equipment.
Yeah.
Right. So anyway, onto the table. Like I said, he did describe. He would number everything on the chart by numerical number, but then through the descriptor, he would say what they were, what the different objects were. And at the bottom, he would list his objects that he found, or that he cataloged, the dark objects that he was cataloged. And then, of course, he produced a chart for the region, which is always nice, because he highlights his, there's the little chevron, 355, 349, and then 2 above the North American. So, great finder charts, really useful if you're looking for these, and of course, the chart on the plate. So, it's a great resource, it really is. So, all of this led to me doing this project to put a page in the handbook. Dick Cairns' idea was to someday have a page in the handbook for dark nebulae, because there never was any. And it died, and like I said, I got this idea when I got back into observing. I got my telescope. The first thing I wanted to do when I got my new 12 average telescope was finish the NGC list, which I did within 3 or 4 months. I had 3/4 of it done before I got back into it. And my goal was to get it done in time for the London GA in 2001, because I knew I was going, and I wanted to get my certificate of the GA, and I got my certificate standing beside Stan, because it's an SA certificate. So that was always nice to do too. Nice to do things with friends. But once I was done the NGC list, I was back to the old age question of, what do you do now? What do you look at? There's the Herschel 400, there's the NGC list, there's other things to look at. But I was digging through my logbook and a page fell out. The page was this old list from Dr. Cairns, dark nebulae. I said, that sounds like a neat idea. I should see if they'll let me do that. So that's what he did. I asked him, he said, yeah, go with it, run with it. Here's all the information I have on it. And I went out, and in about 3 years, I observed roughly 150 of Bernard's objects, of the 280 or 300 odd objects that are on this list. And literally picked out the best ones as I was going through the list and finding what was easy to observe, and visually going out, looking, and finding which ones really weren't easy to observe. Some were difficult, some were easy. It just kind of tabulated a list of what seemed to, what were nice, what would people be able to look at, and that's where it came from. We added a few in there that weren't Bernard's objects, mainly LG3, the Beverly Lynn's 896. Notice they're up in Cygnus. The Northern Coal Center, for example. Some of the significant ones that are elsewhere. Most of them are Bernard objects, and there are some in the wintertime. The majority are in the summer. Of course, it's the Milky Way. So this project was several years in the running. It was fun to do. It gave me the goal every moonless, clear night that I was going observing with friends to do up a target list of these things and go after them. And it was rewarding. I enjoyed doing it. I did. Rajiv Gupta was the observer's handbook editor at the time, and he was encouraging to say, yeah, do it up and get it to me, and we'll go through it. The interesting thing, though, when you're doing a project like this, is you know what to expect when it comes to looking at the objects. You're going to see some of them, you're going to find that a lot of them you don't see. because obviously they're voids. You're looking for voids in the stratum of stars or voids in nebulas. It takes practice, it takes experience, but it can be done. But there are other things that happen that you don't expect, and that's where a couple other things came from. What have I learned from it? Certain darkness is like fumbling for the light switch in a dark guest room. You don't know where it's at, you don't know where you're looking, you don't know where you're going. So you really do need the resources, and that's the biggest thing. You want to start easy, pick the objects for the highest opacity, pick the ones that fit your field of view for your telescope so you can see the entire object in your field of view and have the contrast with the sky around it. Observe it when it's on the meridian. I always tell astrophotographers, don't image that thing when it's 10 degrees on the horizon and rising because you've been waiting 6 months for it to come up. Wait another 3 months till it's up over there. It's going to be a lot better to image. Same with observing. If you observe it when it's just rising, you're looking through a lot of atmosphere, a lot of murk. If you wait for it to be up on the meridian, you're looking through a lot less air, you're going to see a lot fainter stars with nebula, you're going to see a lot more contrast. Thing optics, light pollution filters. You might wonder why, if you're looking at stars. Well, they're not all in stars. A lot of the dark nebulas are actually in the emission or reflection nebula. And a lot of them are in star fields that actually have very low level background emission nebula to them. You just don't realize it's there, or you don't see it. But when you see the dark nebula, you actually are seeing it. I'll mention that again. The last one, take your time. You get to a field, sit there, comfortable in a chair at the eyepiece, and really take your time and let yourself, let your brain look for pattern. Because that's what you're looking for with darkness. You're looking for pattern. You're not looking for a bright object that's going to jump out at you, like the Orion Nebula, for example. You're looking for a pattern. And your brain is really good at picking those out. It just needs that little bit of time. Mention the horse head. Who's seen the horse head? A few of us. Okay. Good. When I got started in astronomy in the 80s, almost every book I picked up told me that dark nebulae were dark patches of gaseous nebulae that were not excited and therefore blocking the light of stars or nebulae behind them. Anybody hear that? Yeah? Everybody still believe that? I did, until I started this project. And I started looking at newer images of the horse head, like this one by the Canada-France-Hawaii telescope of Mega Bright. And then I thought, the minute I saw that, I said, that ain't a dark patch of gas blocking the light of IC434. Because I said, that looks a lot like the Pillars of Creation that Hubble shot in the Eagle Nebula. So, a lot of dark nebulae are actually physical voids in emission nebulas. So this is a region where there's actual stuff, just like here, where there's star-forming region in the nebula. That's what's going on in the horse head. But again, if you want to see this guy, you use a filter. You want to enhance the nebulae so you can see the dark patch. With the horse head, of course, it's an H-beta filter. That's the best filter going for it. But if you're under really dark skies, amazingly dark skies, a UHC, ultra high contrast, and even an oxygen 3 can help. I've actually seen this with both under dark skies. And under really, really dark skies, you don't need a filter. It can be done. The other thing that I learned along the way is that not all charts, atlases, and books are accurate. There are still things that are incorrect out there. And I don't just mean like the NGC list. We know there's a lot of errors in the NGC list. But one of them was, for years, there was this object in the Lagoon Nebula, right here. Kind of looks like a comet. That's what we've known it as for several decades. Robert Burnham Jr. wrote a 3-volume set, Robert's handbook.
Yeah.
Well, it has a copy, probably a bunch of us, right? Yeah. And in there, he refers to this dark comet as Bernard's dark comet. And for decades, people have been going in, looking for this thing, saying, hey, I saw Bernard's dark comet. And then I got looking into the program for the handbook, and I wanted to see it. I went and I looked at it, and then when I heard the Anniversary of 2000 plotted all the objects, one of the things I did is I went through it, looking at them all when I got it, and looking at where they were, which ones were there, and checking it. Sure enough, I went to the lagoon, and I looked at it, and I looked at where B88 was, which is Bernard's 88th object, but that's the one that Burnham referred to as the dark comet. I looked at it where it's relative to these two stars, and of course the center of the hourglass, but then there's 3 and there's 2, and I looked at the chart, and there's a 3 and there's a 2 and there's B88, there's B88, there's the dark comet. My first reaction was the atlas is wrong. They got this in the wrong spot, shouldn't they? Or broke it. I figured this should be down here, so that's where the comet is, off these 3 stars. So that was my first reaction, because this is in the wrong spot. But then I started looking at the images in the Bernard's atlas, and realizing this is probably the object, and this is in the right spot. Saturn, right? This is what Bernard described on the plate for the location, and he even drew B88 as being at the very edge of the lagoon, knocked down with a dark comet. So obviously Bernard figured his object was up there. So Burnham is the one that must have made a mistake. And if you go back and you look at the Burnham handbook, and you look at the plate that he's using for the Palmer Sky Survey, where the dark comet's located, the plate actually crops out most of the nebula. So he didn't have the full view. He didn't have that. He didn't have Bernard's atlas. So Robert Burnham improperly listed the dark comet object as Bernard's 88th object. They're really 2 separate objects. But for decades, we all thought they were one and the same. So the other question came then to me and Rajiv when we were doing this was, what is that object? Because of course, we know now that Bernard's 88 is up here, we know that the quote dark comet is here, but what catalog object is that? And after going through some online searches, we found it's not. It's not catalog. It's not Lynn's catalog. It's not Bernard's. It's not maybe the dark list. So it never really was cataloged. So we just kind of said it's going to have to be known as Bernard's dark comet, as per Robert Burnham. This is a lovely photo. Deborah Sarabola took this one.
Grade 001.
Yeah, grade 1.
So, sorry?
Grade 001.
Yeah.
Grade 0, no, it's not mine. Burnham Jr. is the one who found it. He's the one who brought it to light. So that's what we say. But again, this was a counter photo from a couple of years ago. Counter photos are great finder charts. They do work. I have photos from the 90s out of the calendar that were great charts that I used as finders. They really do help because all these little things are visible in the telescope. They're good skies. So again, we went on to basically say that the dark comet is Burnham's dark comet, not Bernard's, because Burnham's the one who brought it to light. But yeah, that's kind of where it's at. It's kind of neat to find out that things aren't always what you thought they were. The books aren't always right. So back to that squiggly thing that we saw earlier in the chart. Yeah, there it is. It's along. Does anybody have any idea what that is or where it's at? This is the lizard, Bernard's lizard. He actually describes it as a lizard in his atlas. And it is down in the very eastern wingtip of Aqualia. Sorry, eastern western wingtip of Aqualia. It's 4 degrees long, it's a binocular object, and under truly dark skies, it's a naked eye object. It's a nice crescent shape. So, that's his photo. That's my photo. That was taken about 5 years ago. Just wanted to shoot it for another talk that I was doing at Starfest. But there's the lizard. There's the head, a couple legs, the long body, the tail, and the other legs are back here. It's and of course the wingtip of Aqualia is up here. I believe this is the bottom of the wing. And you can see the edge of the star cloud, the Aqualia star cloud, in the Milky Way. You're right in the heart of the Milky Way. trivia minute. Anybody know where this is at? Go forward one slide. Anybody know where this is at? Go back. 100 years ago, nowadays. So we'll put them side by side. Same scale, different technology, different techniques, 4 to 5 hours, manual guiding, probably auto-guided, probably 2 or 3 or 4 hours of data, probably 5, 6, 7, 8 hours of processing. I think Bernard might have had it easier. No, it's colorful, but just as deep, just as much detail there. The dark nebulae are there, there's the S shape, and there's the S shape there. The little comet shape is in there and in there. So this is the large nebula of the IC 1396 up in Cepheus. You see Cepheus? And we all know a lot of astrophotographers image this. It's a great target for wide field imaging. But it's also a great target for visual work. You can go in here and you can see most of these dark nebulas. They don't jump out at you, but with a filter they do pop out. And when you realize when you're seeing this, or you're seeing this, or you're seeing this, you're not seeing the darkness. You're seeing the nebulosity around it. So you can visually observe IC 1396 by looking for the dark nebulous. The object is too big for your telescope to fit in one view. By searching out the dark nebulous within the objects, you're actually observing that large IC object. Another challenge for those out there who like to go deep, challenging deep sky objects. And there's the chart for the area. You notice that the large circular object of 1396 is not shown, but all the dark areas within it are sketched out. It does show a bit of the velocity here, up here. And to give you an idea, on this chart, I observed every object I get on this chart. So it can be done. There's lots to do. So what was next? I mean, I finished the project, we got the thing in the handbook, that was great, we got a list. Of course, there's always the, what I'm doing now, encouraging others to go and look at nothing, because we'll see empty spots in space. But also there is been a request a number of times to expand this section in the handbook. There are hundreds of dark nebulas out there that are worth looking at. It's just a matter of having the time and the energy to do a project and go do it. Complete visual observation of Bernard's dark nebula list. That one's been on my mind since about 2001 when I started this. As I kept picking them off, I started to realize this should be doable. So I want to go through and I want to see them all. And last summer I was talking to David Eicher at Starmus, and we were talking about this because he's a big dark nebula guy too. And he said he doesn't know of anyone who's ever done it. And I haven't heard of anyone else who's ever observed all of them visually. The other one that's come up, I'd say recently, but it's not, about 5, 6 years ago, was this last idea. Image the entire catalog. Which we kind of need to do. And I put it off, put it on, put it off. Peter Jedicke from the London Center has been having to do it for years. So I finally got around to doing it. I wonder why a hologram has anything to do with that. After moving back to the States, my wife and I, our one child, Catherine at the time, we ended up moving back to New Brunswick, and then we had our son Nathan, who's 14. We have a set of twins that came along after him by surprise. They're now 9. So life was busy. I did a lot of imaging, well, observing and imaging in New Brunswick. It was nice. I could go out the door, set up on the deck, and it was convenient and did really well. But it's also a lot of work to set up and tear down all the time. My wife grew up in Kentfield, Nova Scotia, which is in the Annapolis Valley, for those who know the area. It's arguably the best agricultural region in the province. The rest of the province, for anyone who's been there, knows it's mostly Appalachian mountains that have been formed roughly 1 billion years ago and been slowly eroded and ground down to bedrock by multiple glaciations. And if it's not bedrock, it's probably glacial tip. So if you go to dig, you're not digging far, because it's just solid rock. But in the valley, I could dig a 4-foot hole with a post digger and not hit a rock. So it was a real joy. And out here, I'm sure you guys can all do that with post diggers, but down home you don't. So, guys in Halifax, they did not like it when I told them about this. They blast. That actually dug a hole 2 feet diameter. I went down 4.5 feet to drop a 2-foot footing down there. Dropped in some posts and started my observatory. Lifelong dream, right? Backyard observatory. So this is the other part of the talk, was try and encourage people to get out and observe, but also if you've ever been thinking about an observatory, you'll probably take interest in this, and I hope you get just that extra little push to say you're going to finally do it. But I just dropped a pyramid. I dropped in 6 posts for footings to hold the deck that I'm going to build on. It's easy going. This was actually the fall of 15 that I did this. I put the deck down and I stopped. I actually wanted all the posts on the pier to settle over winter before I did anything else. Hoping it wouldn't move. It never did. The frost line this year, I don't think it exceeded 6 inches. But most years we do go 4 feet when we dig footings because our typical frost is 3 to 4 feet below grade. Give you an idea how mild a winter we had this year. Actually, 3 weeks ago I had to replace my lateral from my house to my septic because the old pipe rotted and basically dropped where it entered the septic tank, so that the top 10% of the pipe was going in, but the rest wasn't. And I went out with a shovel and I dug up my septic tank, and then I went back home, and in about 20 minutes of work we dug up the entire line. There wasn't any frost in the ground. Really nice to have to do that in the winter, not have frost. But it was nice because nothing settled. The next spring is when we got the real work on it. This was a beautiful spring day in April. My youngest daughter was 6, so I stayed home with her because she was home from school. I spent the day laying deck. It was also the day the monolith showed up. You're probably wondering why it's so black. Two things here. On top of all my beams, all my floor joists, I laid some of this material. It's basically roofing paper, just to keep the moisture from laying on top of the joist and for the floor. And then what I did is I went to the hardware store and I went to the mist tint section and I found a gallon of mist tint stain. And I stained the bottom of my floorboards, my sheets of pressed wood for the floor before I laid them down. So the underneath is stained to protect the moisture coming up. Also, you see on the gravel, I dug down about 6 inches. I laid down a 6mm vapor barrier, covered the gravel as well to stop moisture from ground coming up through. And to this day, the gravel's been dry as a bone. I've never had a day where that's been wet, so there's no moisture underneath coming up. That was my daughter that stayed home that day, so she helped me. She wasn't feeling too sick by the afternoon and wanted to come up and enjoy the sun. But, it's 8 by 12, nice size. I was able to start using it because, of course, once the pier was in, I had the plates on, so I was able to just take the mount out and drop it on, and I wouldn't leave it there. Looking south from my location, this is looking down the backyard. This is actually the pond in my neighbor's yard. We normally skate on that until now. It's thawed. There's not a drop of piece of ice in it. It's water. But my southern horizon, other than these couple trees, down through the gully here, across, I have about 5-6 degrees on the south mountain from the valley view. Looking south, south of me is nothing. I have 40 miles of center of the province across, where there's woodlot. At the other end of that 40 miles, the town of Liverpool, might be 5,000 people. You go south of that, you go to Bermuda. So there's nothing. So nice dark spot. Started framing, that went fairly quick in one day. The only thing of interest you might notice, I left a jog in the wall at the end here and on the other side. I noticed I had the mount on. It's going to be a clear night, so I was going to use it that way as it was. And I started building beams as well. We'll go into these notches. I'll show you in a second. So for runners, I built the beams out of pressure treated. I actually took 2 2x6, sandwiched them together, glued and screwed vertically, and then on top is a 2x4 horizontally, glued and screwed again to the 2 2x6s. That way neither of them can twist left or right or up or down. So it's basically a built-up beam. The notch, of course, was for the beam to sit into, so that I could screw glued and screwed up from underneath in the end into that beam, so that the outlying beam is actually part of the integral part of the wall. So if there is ever any frost, it won't twist much. It'll hopefully keep the alignment well. The roof wasn't as hard as I thought it would be. I'm not really a carpenter, so it's kind of neat to do this all by myself. I am a civil tech by trade, mostly in wastewater and water, though, not in this kind of work. But I know enough to be dangerous. We don't have the snow load that we have here, so very low slope roof was all I needed to keep it nice and light. Didn't need a lot of trusses. You notice it is running on 3 wheels on each side. I was going with a sheet metal roof. I'll show you the wheels first. What I did is I went with a V-groove caster wheel, and I ran it on 1.5-inch angle iron that is inverted. So the grooves run on top of the angle. I screw the angle iron down at each end, and then every 6 inches alternating down with stainless steel screws and washers, so they won't rust out. I never did paint the stainless or the angle iron. I'm not too concerned about it. It looks exactly like the way it did when I installed it. Suddenly rusted. The beauty of this system is it won't bind. I've had friends who built observatories with garage track and door openers. They find if there's any frost in the wintertime, they get the slightest, 1/4-inch, 1/2-inch aluminum in the wall. They go to push that roof, it binds. Get that little bit of jamming and binding in the walls. This system, these wheels float on top. If there's any binding or problem, they'll ride up and down. So very low rolling resistance, easy to go. Once I get it started, I walk with one hand. 8x12 roof, sheet metal, no problem. Just roll it off, even in the winter. The other beauty with this, you can paint it black if you want. I never got around to doing that. I might do it yet. But I've yet to have any significant snow stay on top of the rails outside of the roof in the wintertime. There's just enough heat, both inside the observatory from solar heating on the sheet metal roof, that these stay warm enough that there's just enough sunlight that when they do get exposed, the snow melts off really quick. It's just like a railway track. That's the last thing the snow sticks on is the railway track, it melts around. So it works fairly well for that. How do I keep the roof on when I'm not down there? Very simple. 4 turnbuckles, 1 in each corner. They're 3/8-inch turnbuckle, bolted into that laminate beam. The beam I built for the wheels is, again, it's a 2 2x6s with a 1/2-inch piece of plywood in the middle, glued and screwed together. So that allowed perfect fit for the V-groove caster base. Just 4 3-inch leg screws right up into the bottom. Real easy to go. And then the bottom, on one end, the eye for the roof is screwed into the top plate. At the other end, they're actually screwed sideways into double studs on the end wall. So the roof's not going nowhere. Even in my backyard, the worst of the nor'easters we get, we might get 80, 90 click winds, and I haven't had a problem. I haven't had a problem with snow going in either. I overlapped on the other side. The other good thing about that beam is it gave me a nailing surface for my other side board to overlap. It gives me about 1/4-inch to 1/2-inch airspace between the wall and the overlap. It actually is very good. It provides good airflow through the building. It stops the sweating when we get extreme temperature changes in the wintertime and spring. So that's with the roof open and with the roof closed. You might think, why does the roof stop where it stops? I could have ran it out farther. I could have designed it to go further, but I didn't need to. You notice the trees in this is actually my west. And just to the right of the hostas, there's a, I don't know, maple tree that's probably 2.5, 3 feet across. And it's not going anywhere because I'm tapping for sap every year. So it's staying. But by the roof going to where it doesn't actually limit my sky because the trees beyond it limit more than the roof. Just as easy. And with the roof closed. Took me, to get to this point, I was about 2 months, working 1 day on the weekend each weekend when I got the way to pick at it. 4 kids at home, they're all in school, plus we work, both my wife and I. So, pick at it when you can, right? But it's not too bad. Sheet metal roofing was really easy, really light. So what's inside? This was very early. Actually, this was last year after I got the new scope. When I designed the observatory, at the time I had a HEQ5 mount, and I had a Stellar View 70 little Oppo refractor. I did have a C8, orange tube C8, and I basically built the walls at a height that would allow me to mount my old HEQ5 and the C8 or the refractor, so that they could get down to 10 degrees above the southern horizon, above the wall, and the roof closed over top of them. So those 6-inch beams that I had the wheels laid to, just raised my roof rafters enough to clear those slopes. I never thought I'd ever have a bigger scope. I figured that's what I'm going to have in here. I might go to a 4-inch refractor, that'll still fit. I never thought I'd end up with 7.9-inch back suits off Newtonian. I always dreamed of having one, didn't think it was going to happen. So when I got the Mac New, my first problem was I can't park the mount with the Mac New on and close the roof. So that's going to be a problem. But, which means I'd have to do an alignment every night I go out, which, as Kevin knows, is a pain in the butt. You know, it's a lot easier to go and say start from perk, and it knows where it's at, and it goes where you want. It saves time. A few other things I did of interest inside. I don't use the lamp often. It's mainly there if I need it for setting up and tearing down. You notice there's a bit of a rope plate here. It kind of goes up under a ledge. I nailed a piece of strapping to the wall, and then underneath the strapping I put the rope light. And then I put a 4-inch piece of plywood over top of that. So I could turn on the rope light, and I have this downcast red light on the wall, and it's on a dimmer switch. It's LED on a dimmer switch. So if I have guests down there, whether it's my kids or somebody who comes over that wants to look, I can have a little bit of light down there on the floor so they can see when they're walking around and not bumping into stuff. Quite often when I'm observing, I don't have it on at all. And the speakers, I get some real speakers down there, but for now the old computer speakers work. It's nice to have music when you're alone in the dark and it's cold. You hear every crack and creak in the ice and snow and what's up there. We all have stories probably of wildlife coming to our observing sessions.
Yeah.
Yeah, you know, we have one guy in Halifax, our club observatory, Darren Talbot, who stands about 6'6". He was hit by a bat one night. A series of rabies shots, not fun. And one of our other members kept hearing a noise, and he figured it was the deer grazing over on the edge of the parking lot. And then he kept hearing the noise, and then he heard this other noise. What's that? He turned around and shone a flashlight over the wall of the observatory to look over at the parking lot to see where the deer was. The deer had both hooves up on the wall, was looking at him. He said he wasn't sure who scared who more. Both jumped. At least they can't hurt you, right? Although I would be afraid of a buck deer, especially in the run. So yeah, that's basically the way I had it when I first set it up. I'm still working on the inside. I'm still doing a few other things. Most importantly, last September I ordered a new mount, sold the HEQ5 and bought an EQ6 because with the scope kind of fell in my lap. That's a whole other story. I couldn't turn it down, and I realized I wasn't going to get rid of it, which means I need a bigger mount. So I got the EQ6, which is now in place. And the beauty of the EQ6 is the new software package and hand controller is a custom home position. So when I park my scope at night, this is the way it parks. I have 2 inches of clearance above my finder scope. I can close the roof now partly. So it's really nice to have that custom park position. I still have cable management to do. That's been done. And the other thing is the firewall is now black. I am in the process of painting all the walls. The other thing I'm doing on the walls is I'm putting one sheet of plywood on the wall, but not to the bottom, not to the top. I'm painting the top foot inside, top and bottom, flat black, and then I put the plywood up and painting it flat black. But I'm leaving that wall cavity open at the bottom and top for one reason. I don't want it to be closed. If it's closed, it will hold heat. It will heat up from the outside, from the sun, and it will stay warm through the night. This way, airflow constantly goes through there, daytime and nighttime. So it allows that heat to get out of your wall and you don't have that heat sitting beside your telescope that you're looking over when the nighttime comes. So eventually I'll close in the other walls too. And eventually I'm going to paint the roof black as well, at least the end of it that's close to the observatory and where I'm working. How many minutes on time?
Good for another 10 minutes.
Oh, perfect. Yeah, that's good. So as you can see, I am imaging with a DSLR. My Canon stays on there almost all the time. When I go out to take family photos, I grab my daughter's, which is my old Canon. But she doesn't mind because she has the freedom to use all my lenses. So it's kind of a trade-off. So I am doing imaging. This is what Kevin wanted to see, I think, was pictures. I'm nowhere near what Kevin does, others in the calendar. I always wanted to get a photo of the calendar. This year I do have one of the calendar, but it's not deep sky object. So we'll get there. But yeah, the Pleiades, that was taken in the backyard. I have decent skies on a typical night. The limiting magnitude is 5.8 or 5.9 out of the backyard. And those fall nights when you get the clear, transparent, dry Arctic air come down, I can see 6.1, 6.2 some nights. So it's a decent backyard. That was my clay shot from a year ago. Last fall I shot at 51. That's my best at 51 shot so far. Still pretty grainy, a little noisy. Needs another 2 or 3 hours of data. That was about 2 hours there, so not bad for a DSLR. But it goes to show that with even a DSLR backyard telescope, you can do some decent imaging. My best fail shot today, that's actually about a year old as well. And what I'm really pleased with the M51 shot and this shot is they were both with the previous shot was with my old stellar view. So you can see the difference in the stars just if I go back. The stellar view, they're a little bloated. You see a little bit of the diffraction from the dirt on the lens. It was pretty cruddy at the time. Well, it wasn't the cleanest of optics. But when you go to the Mac, the star image got a lot smaller and a lot tighter and a lot cleaner, especially there. Clean up really nice. So I'm very pleased with the Mac. I'm glad I finally got one. I nagged Peter Ceravola for about 10 years after he stopped making his to make me one. He never would do it. So he said he was glad when he found out I got one too, because I'd stopped nagging him. Going forward, I do shoot a few other objects. I do some lunar work. I'm currently working on the Isabel Williamson lunar program that the Society has. I'm about halfway through it. The beauty of a backyard observatory is it's always there. So if you get those nights that are cleared, you've been desperate to get out for a night or get out for an hour in of looking, and the moon's up, well, I'm not going to take an hour to go set up all my gear. But when it takes me 5 minutes to unblanch the roof and roll it off, it's easy to do. So it's easy to go out and spend a half hour, an hour, and close it off and go back in.
Hallelujah, brother.
Was that today?
Hallelujah.
Yeah. The best part of a backyard observatory, from the time I decide I'm tired, I want to go to bed, to the time my head hits the pillow is 5 minutes to shut down. That's really nice. So yeah, this is an image I took of the moon last March. There's a lot of better ones out there, but I did put this one in the calendar. I finally had something I thought was good enough for the calendar. We don't often get many submissions of just a shot of the moon. Hint, if you want to do something different, it doesn't have to be deep sky, you can do the moon. But the reason I put this in is also because I want to show how simple it can be done. Before I go on with that, just to show you some of the detail. Copernicus down here, there's 3 or 4 crateroids easily in that. If you look really close, the dark wall, the Great Wall is right there. Put that on. They were showing nicely mounted along the mountains. Peaks are really nice. It's actually a real nice sharp image. It's a single frame image. This is not video. This is not stacking. This is not overly processed. This is a single frame image under ideal seating conditions through a decent set of optics. That's all it was. I took about a dozen of them. This was the best. Just grab that 1/100 or 1/150th of second exposure, and off you go. So you can do decent lunar imaging without having to deal with the video and all the software processing. It can be done. And I've seen people doing it. We got a guy in Halifax who does almost the same stuff all the time with a smartphone. It can be done. So don't be discouraged by seeing thousands of dollars worth of ads for equipment. You don't need it all. You just need a decent scope that tracks at the lunar rate, which most go-to maps do, and time under the moon. And I played with planetary imaging a little bit. 3 nights so far, I think I've done this. This was the first night, actually. This was the best night. It's nothing spectacular. It's no Damien Peach work for sure, but it's Jupiter. We all recognize Jupiter. It is the red spot. There is a lunar shadow. If you look closely, there is Io coming off the disk. And this is the first night I really played with this, and I toyed around with it. It was a real nice night. It was warm. It was comfortable. Sitting down there, I said, you know what, I'm going to keep going, and I'm going to switch over here for a quick second. To show you, with about 2 hours of sitting there, shooting video every 5 minutes for 30, 40 seconds, you can create a little animation. It's not the sharpest in the world, but I was pleased. So that's planetary imaging by me. That's all I've done so far. But I'm happy with it. It's it goes to show it can be done. You can see the stuff. Kind of neat. So why build an observatory? Easy to go observe. So I've had 75 nights in my observatory since I started January 1st of 16. The 3 years that I lived at that house before that, I had 5 nights of observing. That's how much it's changed for me for observing. It's gotten me back out there all the time. It's not always imaging. I got that pier set at one end of the observatory, so my 12.5-inch dog is at the other. There's nights where it can be imaging and I'm observing, or the nights I just go down and observe. Some nights I just go down and look through the back window at the planets. I have that choice, so it's really nice. And storage. My wife loves the fact that I no longer store all my telescopes in the house. But I only got the 2, but still, between the 2 of those, the mount and all the other gear, they're not in the house. And I kind of like that too, because I used to store half that stuff in my closet because she didn't want it out in the room and in the house. I don't blame her, but it meant that I didn't have much closet space, so it's nice to have. So on to the last little bit of the talk here, I wanted to go back to the dark nebula to wrap it up. I mentioned the plates and the charts. Well, like I said, Peter Jennecke's been after me for years to pursue that imaging project. I finally started this year by doing some tests. And I started this winter, so I had to find some of the plates that were winter areas of the sky. One being Jiminy, Messier 35 by Mr. Bernard, 100-something years ago. And the same region of the sky by me a couple months ago. What do you think I shot that with? Any guesses? I can. Yeah. With an 85mm 1.8 portrait lens. Stock Canon lens. So, yeah, there's a lot of detail there. There's even a little bit of the blossom in here.
Is that the art lens?
Is that what?
Is that the Sigma art lens?
I'm not sure if that's what that is or not. I never
No,
actually
the
checked.
lens you used.
I never checked to look. I never
Okay.
looked at an atlas to check. So honestly, I have to look it up. I shot it mainly to get M35 into the star field to see what it would be comparable to the atlas, and that's all I did with it.
How long was the exposure?
That's 61-minute shots, so 60 minutes. And about 30 minutes of dark frames and some lights and bodies. And then I processed it myself. Mostly in PixelSight, I believe. But, I mean, I was happy with the result. It goes to show that with the 85mm lens, and I did crop it at about 70%. So I am cropping off the other 20-30% of the field. And I'm cropping it square so that I'm matching scale size of Bernard's plates as well. So this is my next project, is to go through some of these. So the other areas I did, there's no dark objects on the other one, but there are near Messier 37, B34, B226. If you ever go look at the Messier objects in Riga, this guy is easy. If you go look at M37, go look for this dark nebula. Get the chart and go look for it, because it's a black spot. It's right there. You probably didn't know you were looking at it if you ever looked at M37. But going forward, there's his shot of M37, and there's my shot. And there's that black spot. Other than the fact that it's not black and white, it's pretty much the same. It's actually probably a little deeper than what Bernard shot. And then the last one, and this one's a little more interesting. This will be the last 3 slides here. Orion. Anybody recognize the part of Orion this is in? This is the head of Orion. This is Bellatrix. Betelgeuse would be over here. So there's 1, 2, 3, a couple dark objects up in here. And he's got one labeled here, B223. You notice it's not just circled, it's hazed in. That threw me the first time I saw that in the chart too. And again, it's filled in. And when you read his description, he's not actually describing this, but he's describing the space around it. What it is that's an actual reflection nebula. He's describing the void around it by, you see it because of the contrast to that, which is different from what he's normally doing. But you can see the objects. There's the real dark one there, there's the line down there, and then there's stuff up in here. But again, his shot, my shot's a little, not a lot. This was the first one I did, and I should have showed it first because it wasn't the first one I did. There's two things wrong with it. One, I didn't have the camera quite lined up north-south, so if you look back at this chart, this is a little more straight up and down to here, and go forward. Mine's a little twisted to the left, over the clock. But also there's this fictitious nebula up in the corner. And I look back at his plate and I'm like, there ain't nothing up there. I look at his chart, there ain't nothing up there. And I look at my image, what the heck is that? I finally figured it out about a week ago. I have a UV filter on the front of my lens. It's a reflection internally inside of that filter. The other shots I did have the filter on, never showed up. So that's all that is. So I know going forward I need to keep that filter off when I'm shooting star fields that have a bright star, because it's directly opposite halogens. But you can see all the dark nebulas are there, and there's the one there, and there's the line down there. You actually notice this one's not a black void like in Bernard's. There actually is a bit of a brownish to it. It's dusty. It's just got exposed long enough to get. And there's the reflection nebula. That's actually one of the Beverly Lend objects. So that's my next project. I now know I have the equipment, the location, and the right lens that I can frame and match chart for chart, or plate for plate, what Bernard did. My goal now is to go through and do all 50 plates. Do the opposite. So, with that, I'll finish up and say thank you.
Maybe we have time for a couple questions if anyone has any. Yeah, go ahead.
What's your favorite eyepiece to look at the dark nebula?
It depends on the object. It really does. Some of them that are 1, 2, 3 degrees in size, my old go-to is a 32 millimeter wide field, television wide field. I just had one in my box for a couple decades. It's there. I would love to have a 35 pan to do the same things. Buddy of mine used to have one, so I borrowed his a lot of the time, and we observe them together. But if you're really looking for them, you really got to match your field of view for the object. So it really depends on the object. Probably the one that stands out the most that I get questions about is what do you use to look at the horse head? And I tell people I have a 25 millimeter colossal. Honestly, I do. I have an F5 telescope. 25 millimeter on the F5 gives me a nice, I believe it's a 5 millimeter X pupil. But at the magnification of the X pupil, you get the highest contrast for the object. The horse and the size it is, with the velocity in a field of view. If you go to a higher magnification, you're actually reducing that contrast. If you go to a lower magnification, you're reducing the size of both of them, and it's harder to see. The 25 millimeter eyepiece on an F5 telescope is the horse head eyepiece. That's the magic eyepiece for any F5 telescope. The other reason I go with a colossal, it's the least amount of glass that gives me a decent view. So I want as much transmission as I can get. So the horse head is 25.
Thank you.
Jerry, do you have your hand up?
Yeah, your pictures convincingly show us that the more stars you can put in here, the easier it is to see these dark nebulas. So how big a scope should we want to use to start looking for these things?
Depends on the object. Again, some of the larger dark nebula, some of the easier ones, I would say, if you go to the handbook list, look for the ones that are the easiest dozen of those 38. And you can start with a 4-inch scope. I have a 4-inch f4 Taylor Hobson television camera lens that has a 1 1/4 inch focuser machined onto the back. And I've seen well over 100 dark nebula through that little scope. It's a rich field telescope. There's a pair of dark nebula in Sagittarius or Sagittarius. Yeah, down in Sagittarius. Can't think of the numbers right now, it's slipping my mind. But they're perfect for a rich field telescope. There's a lot of, I mean, most of the prancing horse, you want a rich field telescope for a pair of probably 7 by 50 or 10 by 70 binoculars. It's the best thing for it because the field of view is just perfect for framing all of that stuff. And now, if you want to look at the S nebula, the B87, the S down in the prancing horse, it's only 30 minutes in size. So you want a field of view of about a degree. But, so then you don't want a rich field telescope. You want probably a 6 or 8 inch or a larger dome or a larger reflector or something of that size to pull it, because that particular nebula is all stars. You're just looking for stars. You need pinpoint objects to get those faint stars pulled. But yeah, they all vary.
And to do the whole Barnard's list?
I want to do the whole list. I expect there's going to be a handful of objects I'm going to need a 16 or 18-inch telescope for. They're objects that are inside the velocities that are that faint. They're difficult. Like I said, the Horsehead is a difficult one. If you think the Horsehead is difficult, try that check mark up in the North American. It's just as bad. And there's a few others out there like that. But a lot of them are easy. A lot of them are, it's just get the skies, get the optics.
And you got to know they're there.
Yeah, you got to match your field of view and your light gathering with the object, and you got to make sure you have a chart so you know you're looking at it. But they can be done.
Alright. Good. Alright, well, as a token of our appreciation, I've got something that you probably enjoy, like to eat. Don't eat this. Thank you very much. Okay, so as usual, we'll be continuing our meeting at Boston Pizza, over beers and pizza. I should warn you that there is a reservation in our spot that started like about an hour and a half ago. So I'm hoping that they're out of there by 10:30. I mean, I don't work there, you know. But I was told that they were hoping that they would be out by that time. But if you show up and we don't have our spot, we might just have to wait a little bit. So, other than that, one item that I forgot to mention in the announcements, we had a recent council meeting and we're looking for members who would be willing to run workshops, more hands-on workshops outside of our regular meetings. So if there's a particular area of interest that you have, we'd really like to get some people who have some hands-on expertise, knowledge, and we're thinking more like, you know, rather than like a setting like this, more like a setting where, you know, we have a few tables, a handful of people. So anything from you know, scope collimation to you know, to building your own telescope to you know, astrophotography stuff like stacking, those sorts of things. So we're looking for some people. If you are interested, let me know, and we'll try to set something up. So thanks very much. You guys